June 20th, 1944. The floating harbour at Arromanches, Normandy. Royal Engineer Lieutenant Colonel George Shadic stood on the pier head of what his men called Port Winston, watching the 7th Liberty ship of the morning manoeuvre toward the loading wharf. Behind him, an endless column of lorries rumbled across the Whale roadways, their steel decks rising and falling 15 feet, with the tide yet maintaining perfect horizontal alignment. The harbour that experts had declared impossible to build was handling 6,750 tons of cargo that day, and tomorrow would bring 7,000. The mathematics seemed absurd. Dover Harbour, Britain's busiest cross-channel port, had required 7 years to construct and covered 310 hectares of permanent installation. The floating harbour at Shadic's feet had been assembled in 12 days from components towed across mine-infested waters, occupied less than a third of Dover's footprint, and was matching its discharge capacity while anchored to nothing but sand and tide. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German intelligence had dismissed such a harbour as physically impossible. The Atlantic Wall's entire defensive strategy rested on one assumption: invading armies required capture of a fortified port within days of landing or face defeat through supply starvation. Yet here floated proof that engineering ingenuity could rewrite the rules of amphibious warfare itself. The real victory wasn't the harbour's existence. It was the systematic destruction of every assumption military planners had held about harbour construction for 3,000 years. The transformation had begun on May 30th, 1942, in a War Office conference room in London. Winston Churchill had just finished reading reports from naval architects explaining why artificial harbours were theoretically interesting but practically unfeasible. The explanations cited fundamental physics, tidal mathematics, and centuries of maritime engineering precedent. Churchill's response, preserved in the meeting minutes, cut through the technical objections with characteristic impatience. If ports are not available, we may have to construct them in pieces and tow them in. The room erupted not with enthusiasm but with polite skepticism barely distinguishable from contempt. These were men who had spent careers designing harbours. They understood the immense forces that waves exerted on fixed structures. They knew the impossibility of anchoring anything substantial to shifting sand. They recognized that tidal variations of 20 feet twice daily would tear apart any floating roadway strong enough to support loaded trucks. The very suggestion violated everything their training and experience taught them about harbour engineering. Yet that evening, Churchill issued a directive to Admiral Louis Mountbatten that would launch the most complex construction project of the war. The memo consisted of 60 words that transformed impossibility into orders. Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. The final sentence embodied Churchill's understanding of engineering culture. Given the task without permission to debate its feasibility, British engineers would solve problems they'd previously declared unsolvable. Don't argue the matter wasn't dismissiveness. It was psychology. The next morning, the War Office's chief engineering staff received instructions to form a technical committee. Their assignment was to design, build, and deploy 2 complete harbours, each with capacity equivalent to Dover, that could be assembled on hostile shores within 2 weeks of D-Day. The deadline for initial designs was June 30th, 1942, 30 days. The problems seemed to multiply faster than solutions. How do you create a harbour capable of handling 500-ton Liberty ships in water where the seabed offers no bedrock for anchorage? How do you protect that harbour from Atlantic storms that generate 8-foot waves and force 6 winds? How do you build piers that remain level while floating on water that rises and falls 20 feet every 6 hours? How do you construct roadways strong enough for 30-ton tanks, yet flexible enough to accommodate that tidal range? How do you transport 600,000 tons of concrete and steel across 100 miles of open ocean? How do you assemble such structures under German artillery fire? Each question spawned dozens of subsidiary problems. Yet the strategic necessity left no alternative. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The first serious proposal came from Hugh Ioris Hughes, a 40-year-old Welsh civil engineer who submitted plans on June 17, 1942. Hughes had spent his career designing concrete bridges and underwater foundations for Owen Williams's engineering firm. He brought to the harbour problem a deep understanding of how concrete behaved in water and how structures could be designed to exploit rather than fight tidal forces. Hughes's breakthrough was conceptual rather than merely technical. Traditional harbours fought the sea by building immovable structures anchored to bedrock. Hughes proposed embracing the sea by designing structures that moved with tides and waves rather than resisting them. His initial sketches, preserved in the Institution of Civil Engineers archives, showed massive concrete caissons that would rest on the seabed through their own weight rather than mechanical anchoring. The caissons would be hollow boxes, built on land, floated across the channel, then deliberately flooded to settle them in precise positions. The elegance of the design lay in its simplicity. A caisson 60 feet high, 200 feet long, and weighing 6,000 tons when complete would be light enough to float when empty, but heavy enough to resist storm waves when flooded and resting on sand. The internal chambers could be flooded in sequence, allowing engineers to control the sinking process and achieve exact positioning. Once settled, the caissons would form a permanent breakwater that required no maintenance and no active anchoring system. Hughes called his caisson design Hippo. He coupled the hippos with a roadway system he named Crocodile. The crocs were rigid steel bridge spans that would rest atop the concrete caissons, providing a fixed roadway from offshore anchorage to the beach. The system offered brutal simplicity. Sink concrete boxes in a line to create a breakwater. Lay steel bridges across the boxes. Drive trucks over the bridges. No floating components, no tidal accommodation, just straightforward construction using technique Hughes had employed on bridge projects across Britain. The War Office forwarded Hughes's proposals to the Combined Operations Headquarters on June 19, 1942. Admiral Mountbatten's engineering staff began immediately evaluating whether the Hippo Crocodile system could meet the operational requirements. The mathematical challenge was staggering. Each harbour needed capacity to discharge 6,000 tons of cargo daily by D+14. That tonnage requirement translated to specific numbers of piers, specific dimensions of roadways, specific quantities of cargo handling equipment. Working backward from the tonnage requirement, the engineers calculated that each harbour would need approximately 10 piers extending from offshore anchorage to the beach. Each pier would require capacity to accommodate one Liberty ship plus smaller landing craft. Liberty ships drafted 26 feet, requiring water depth of at least 30 feet to prevent grounding. The piers would need to extend approximately 1 mile from the beach to reach that depth. 10 pier, each 1 mile long, capable of supporting fully loaded trucks driving continuously in both directions while accommodating a 20-foot tidal range. The specifications alone filled 200 pages of technical documentation. Hughes's system offered one solution, but it wasn't the only approach being developed. In parallel with Hughes's concrete caisson, other engineers pursued different concepts based on floating rather than sunken structures. Lieutenant Colonel William Teague Everall, chief bridging instructor to the War Office, approached the problem from his expertise in temporary military bridges. Everall had designed Bailey bridges that could span rivers using prefabricated steel sections assembled rapidly by combat engineers. He proposed applying similar principles to the harbour problem: build floating sections in Britain, tow them to France, connect them together offshore. Everall assigned one of his junior officers to develop the floating roadway concept. Major Alan Beckett was a 32-year-old civil engineer who had joined the Royal Engineers at the war's outbreak. Beckett brought to the problem a fresh perspective, unconstrained by decades of harbour engineering tradition. His initial concept, sketched in early July 1942, showed a radically different approach to accommodating tidal variation. Beckett's breakthrough came from observing how bridges failed. Rigid structures spanning long distances accumulated stress at connection points when subjected to twisting forces. The solution used in suspension bridges was to build flexibility into the joints while maintaining rigidity within each span. Beckett proposed applying that principle to a floating roadway. Each section would be an 80-foot steel bridge span mounted on concrete, or steel pontoons. The spans would be rigid enough to support truck traffic, but would connect to adjacent spans through torsionally flexible joints. This flexibility would allow each span to twist independently, accommodating wave action and tidal changes while maintaining a continuous roadway surface. The design elegance lay in its accommodation of forces rather than resistance to them. When a wave passed under the roadway, each span would rise and fall independently, the flexible joints allowing the roadway to undulate like a snake while remaining structurally sound. As the tide rose and fell, the entire roadway would rise and fall with it, maintaining constant elevation relative to the floating pier heads where ships docked. Beckett completed his initial design drawings by July 2, 1942, and presented them to Everall. The response was immediate authorization to build a full-scale prototype. A third competing design came from Ronald Hamilton at the Department of Miscellaneous Weapons Development. Hamilton proposed what he called the Swiss roll, a floating roadway made from waterproofed canvas, stiffened with steel slats and tensioned by cables. The concept borrowed from military pontoon bridges that could be rapidly deployed by rolling them out across rivers. By August 1942, 3 fundamentally different systems were competing for selection. Hughes's Hippo caisson with rigid crocodile bridges represented traditional harbour engineering adapted for portability. Beckett's floating roadway with flexible joints represented a revolutionary approach that embraced, rather than fought, tidal forces. Hamilton's Swiss roll represented maximal portability and rapid deployment at the potential cost of load capacity. Testing would determine which design could meet the operational requirements while surviving the brutal conditions of the English Channel. The Admiralty identified Garlieston in Wigtown Bay, Scotland, as the test site. The location offered characteristics remarkably similar to the Normandy beaches. Flat, sandy bottom, similar tidal range, exposed to Atlantic weather, remote enough for security. In October 1942, the entire area from Garlieston through the Isle of Wythorn was declared a restricted military zone. Local inhabitants were evacuated under emergency wartime powers. A military camp was constructed at Cairnhead to house the hundreds of engineers and construction workers who would build and test the prototypes. The scale of the test program was unprecedented. Hughes supervised construction of 3 full-scale Hippo caissons and 2 crocodile bridge sections at Conwy Morfa in North Wales. The work required 1,000 labourers working around the clock to pour concrete, install reinforcing steel, and waterproof the internal chambers. The largest Hippo measured 60 feet high and 200 feet long. Moving these massive structures from Wales to Scotland required specialised ocean-going tugs and careful navigation through coastal waters. Beckett's team fabricated 6 spans of his floating roadway design at Braithwaite's factory in West Bromwich. Each span was an 80-foot steel framework mounted on concrete pontoons. The torsionally flexible joints used spherical bearings that allowed each span to rotate independently while maintaining continuous roadway surface. The manufacturing tolerances were measured in fractions of an inch, precision machining applied to structures weighing dozens of tons. Hamilton's Swiss roll was manufactured at a separate facility. The waterproofed canvas was wound on massive steel drums that could be transported to the test site and unrolled to create instant roadways. The system offered remarkable portability, but raised immediate questions about structural integrity under loaded truck traffic and storm conditions. By May 1943, all 3 systems were assembled at Garlieston for comprehensive testing. The test protocol was brutal by design. Each system would be subjected to loaded truck traffic, storm conditions, and repeated tidal cycles. Any system that failed under test conditions would certainly fail under combat conditions off Normandy. The testing revealed truths that laboratory analysis could never predict. Hughes's Hippo caisson performed brilliantly as breakwaters. Once sunk in position, they created calm water behind them even in rough seas. but the rigid crocodile bridges proved problematic. The steel spans rested atop the hippos with minimal flexibility. When waves generated differential motion between adjacent caissons, the bridge spans accumulated dangerous stress. Hamilton's Swiss roll failed catastrophically. During a moderate storm with force 5 winds, the canvas roadway tore free from its moorings and washed onto the beach in tangled wreckage. A 7-ton truck attempting to cross the Swiss roll during calmer conditions broke through the canvas surface. The system was eliminated from consideration immediately. Beckett's floating roadway exceeded expectations. The flexible joints allowed the roadway to undulate over waves while maintaining structural integrity. Fully loaded trucks crossed repeatedly without inducing dangerous stress. The system accommodated the full 20-foot tidal range smoothly. Most impressively, when a severe storm struck Galveston in November 1943, with force 7 winds and 8-foot waves, Beckett's roadway survived undamaged. The hippo caissons were undermined by wave action that scarred sand from beneath their bases. The floating roadway simply rose and fell with the waves, its flexible design dissipating rather than accumulating storm energy. The test results drove the final design selection. The breakwater would use modified Phoenix caisson based on Hughes's hippo concept, but redesigned by engineer Oscar Faber for greater storm resistance. The roadways would use Beckett's flexible span design, code-named Whale. The combination would exploit the strengths of both systems while avoiding their individual weaknesses. Part 1. Continued. With the basic design validated, the project entered its most demanding phase. Construction. The scale was staggering. Each harbour would require approximately 200 Phoenix caissons of various sizes, 6 miles of Whale floating roadways, 33 pier heads with hydraulic legs, 70 obsolete merchant ships to be scuttled as additional breakwaters, and 24 massive floating outer breakwaters called bombardants. The total material requirements exceeded anything Britain had attempted. Over 1 million tons of reinforced concrete for the Phoenix units alone, 70,000 tons of steel reinforcement, 31,000 tons of structural steel for the Whale roadways, 600,000 tons of total construction when every component was counted. This in a nation already stretched to breaking point by 4 years of total war. From summer 1943 onward, construction accelerated to a pace that bordered on chaos. Commercial construction firms across Britain received contracts for individual Phoenix caisson, Waits Construction, Balfour Beatty, Henry Boot, Bovis, Costain, John Laying and Son, Peter Lind & Company, Sir Robert McAlpine, Molem, Nuttall, Taylor Woodrow. Every major construction company contributed sections. Security demanded that no single firm understand the complete picture. Workers were told they were building experimental anti-submarine barriers or post-war housing components. The Phoenix units were built in massive dry docks, excavated from riverbanks along the Thames and Medway. Each dry dock had to be carved from solid earth, lined with concrete, equipped with pumping systems to flood and drain the dock for launching completed units. The construction sites themselves represented major engineering projects. A typical Phoenix unit required 4 months from excavation to completion. The process began with forming the reinforcing steel cage, hundreds of tons of rebar positioned with millimeter precision. Concrete was poured in continuous operations lasting days, the mixture carefully controlled to prevent cracking during curing. Internal chambers were formed using temporary wooden frameworks that would be removed before the unit was floated. Waterproofing the chambers was critical. Any leak would compromise the controlled flooding sequence needed to position the unit precisely off Normandy. The quality control was obsessive by wartime standards. Every weld inspected, every concrete pour tested, every chamber pressure tested for leaks. The engineers understood that a single structural failure during towing or positioning could doom the entire invasion. There were no second chances. No opportunity to repair or replace a Phoenix that broke apart mid-channel or sunk prematurely because of faulty construction. Arthur Waits, managing director of Waits Construction, supervised building of multiple Phoenix units at his company's yards. Decades later, he recalled the surreal quality of the work. His crews constructed massive hollow concrete boxes according to specifications provided by government engineers, with no explanation of their purpose. The rumor among workers was that these somehow related to post-war reconstruction. Only after D-Day did the truth emerge. They had been building sections of artificial harbours that would change the course of history. The Whale roadway construction proceeded in parallel. Braithwaites and other steel fabricators produced the 80-foot bridge spans to Beckett's specifications. Each span was a complex assembly of steel beams, decking, and the critical torsionally flexible joints. The pontoons that would support the spans came in two types: steel pontoons called beetles, manufactured by shipyards familiar with maritime construction; concrete pontoons, also called beetles, built using techniques similar to Phoenix construction, but on smaller scale. The challenge was manufacturing 16 kilometers of roadway, with each section precisely engineered to connect with its neighbors. The tolerances were unforgiving. A misalignment of even a few inches between spans would create a gap that trucks could not cross. The flexible joints had to be positioned exactly, the spherical bearings machined to specifications that allowed rotation while preventing separation. Testing continued throughout manufacturing. Sample sections were subjected to load tests, fatigue tests, corrosion tests. Engineers loaded spans with trucks weighing far more than expected operational loads. They cycled the flexible joints through thousands of movements simulating years of tidal action. They exposed the steel to salt spray to verify the protective coatings would prevent corrosion. Any component that failed testing triggered redesign and remanufacturing. The pier heads represented perhaps the most ingenious element of the entire system. Each consisted of a massive pontoon approximately 100 feet long, with 4 hollow steel legs extending downward. The legs were called spuds, hence the pier head's codename Spud. The spuds would rest on the seabed while the pontoon floated, creating a stable platform that accommodated tidal changes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mechanism was elegant. As the tide rose, the pontoon floated upward on the spuds, which remained fixed on the seabed. As the tide fell, the pontoon descended. Hydraulic systems within the spuds allowed engineers to adjust leg length, compensating for irregular seabed or storm damage. The result was a pier head that maintained constant elevation relative to the water surface, allowing ships to dock regardless of tidal state. Manufacturing the spud pier heads required shipyard facilities capable of working with heavy marine equipment. The pontoons were essentially small ships, requiring similar construction techniques. The spuds were massive hollow cylinders of welded steel, each weighing dozens of tons. The hydraulic systems were precision machinery installed in structures designed to survive storm conditions and enemy shelling. By early 1944, construction was reaching completion. Phoenix caissons lined the Thames and Medway, ready for towing. Whale roadway sections were staged at assembly points along the south coast. Spood pier heads were being fitted out at shipyards. The bombardon floating breakwaters, massive cross-shaped steel structures filled with rubberized canvas, were being assembled at their own specialized facilities. The organization required to coordinate all these elements staggered even experienced military planners. Major General Harold Wernher, appointed to oversee the project, later wrote that the greatest difficulty was the vast number of interested parties who had to be consulted or thought they ought to be consulted. The Admiralty wanted control of anything that floated. The War Office claimed jurisdiction over harbour construction as fundamentally an engineering task. The Ministry of Supply had to allocate scarce materials. The Ministry of Transport had to provide tugs and towing equipment. The Royal Navy had to survey the French coast and mark navigation channels. The Army had to provide anti-aircraft protection once the harbours were assembled. The compromise reached in December 1943 divided responsibility. The Admiralty would manage the block ships to be scuttled as breakwaters, the bombardon floating outer breakwaters, all towing operations, and coastal surveys. The War Office would construct the Phoenix caissons, the Whale roadways, provide anti-aircraft defence, and assemble the complete harbours once components reached France. Neither side was entirely satisfied, but the division allowed construction to proceed. Training the personnel who would operate the harbours presented its own challenges. Royal engineers needed to learn how to flood Phoenix caissons in precise sequences to achieve exact positioning. Navy tugboat crews needed to practice towing massive concrete structures at speeds not exceeding 4 knots. Survey crews needed to mark positions for 200 Phoenix units with accuracy measured in feet, working at night in enemy-controlled waters. The Septcent-Duzeth survey flotilla received perhaps the most dangerous assignment. Operating from HMS Tormentor Naval Base in Humble, they had to collect detailed hydrographic data off the Normandy coast. Between November 1943 and January 1944, special teams used adapted landing craft personnel, large vessels, to survey the proposed harbour locations. The missions occurred at night to avoid German detection. The craft approached within a few hundred yards of enemy-held shores, taking soundings and collecting seabed samples while German sentries patrolled the beaches. On the night of November 26 through 27, 1943, 3 survey craft took measurements off Arromanches, the proposed location for Mulberry B. The mission succeeded despite German awareness of unusual activity offshore. A follow-up mission on December 1st through 2nd to survey the Omaha Beach location for Mulberry suffered a navigation error. The team surveyed an area 2,250 yards west of the intended location. The error wasn't discovered until after D-Day, when Phoenix units were being positioned, and the seabed characteristics didn't match survey data. The intelligence requirements extended beyond hydrography. Engineers needed detailed information about beach gradients, soil composition, tidal patterns, wave characteristics, and storm frequencies. The government actually appealed to the British public for holiday photographs and postcards of the French coast. Tourists who had visited Normandy beaches before the war unknowingly contributed to invasion planning by providing their vacation snapshots. With construction nearing completion and D-Day approaching, security became paramount. The entire project had proceeded in secrecy for 2 years. German intelligence had observed the construction of massive concrete structures along British coasts, but apparently accepted the cover story that these were experimental anti-submarine barriers. The truth was simultaneously too audacious and too obvious to believe. The Germans could not imagine anyone attempting to build and transport complete harbours across the Channel. A security breach nearly exposed the entire operation in May 1944. The Daily Telegraph crossword puzzle began including words directly related to Operation Overlord. On consecutive days, puzzle solutions included Utah, Omaha, Juneau, Sword, and Gold, the code names for the 5 invasion beaches. Most alarmingly, the solution Mulberry appeared in the puzzle just weeks before D-Day. MySync immediately investigated Leonard Dorr, the headmaster who compiled the crossword. Intensive interrogation revealed that Dorr often asked students for interesting words to include in puzzles. Many students lived near American military barracks where overlord planning was underway. The words had entered Dorr's vocabulary through casual conversation, overheard by students, and repeated innocently. MySync concluded the appearance of classified operation names was extraordinary coincidence rather than espionage. The investigation continued until after D-Day to ensure Dorr wasn't using an impossibly subtle communication method. By late May 1944, over 400 Mulberry components were staged at assembly points along England's south coast. The logistics of moving them to Normandy required 150 ocean-going tugs, each distinguished by large M letters painted on their funnels. The tug crews understood they were part of history's most ambitious engineering project and took fierce pride in their assignment. The towing operations demanded careful planning. Phoenix caissons had to be towed at speeds not exceeding 4 knots to prevent structural damage. The journey from English assembly points to the Normandy coast would require 2 days under ideal conditions. Weather predictions became crucial. Rough seas could damage delicate components or part the tow cables. The tugs had to navigate through mine-swept channels while maintaining station in massive convoys. June 4, 1944 brought the first movement orders. Sections of the Mulberry harbours began to be towed behind tugs and positioned mid-channel, awaiting the invasion scheduled for June 5th. Then, weather intervened. A massive storm system swept across the channel, forcing postponement. The Mulberry components wallowed in rough seas for 24 hours, while Eisenhower agonized over whether to proceed or delay further. When Eisenhower gave the final order to launch Overlord on June 6th, the artificial harbour components were already at sea. In the pre-dawn hours of D-Day, while Allied soldiers stormed ashore under withering German fire, the first elements of the Mulberry harbours were being towed into position. The operation proceeded with choreographed precision despite the chaos of the largest amphibious assault in history. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. On June 7th, D+1. The first Phoenix caissons were brought into position approximately 1 mile offshore from both Omaha and Gold Beaches. Powerful harbour tugs manoeuvred the massive concrete structures with remarkable delicacy, nudging them into precise positions marked by buoys laid by Royal Navy survey ships days earlier. The controlled flooding of the Phoenix caisson demonstrated the brilliance of their design. Each caisson had multiple chambers, with individual flood valves. Engineers could flood specific chambers to achieve exact positioning and orientation before settling the structure to the seabed. The process required hours of careful work for each caisson. Royal engineers aboard each Phoenix monitored water levels, adjusted flooding rates, used compressed air to correct positioning errors. The goal was to create an arc of caissons forming a breakwater with gaps at precise intervals for ship passage. Positioning errors of more than 50 feet would compromise the entire harbour's functionality. As the Phoenix breakwater took shape, it created sheltered water where ships could anchor safely. Simultaneously, 70 obsolete merchant ships moved into position for scuttling. These vessels, codenamed Corn Cobes and collectively creating the Gooseberry breakwaters, had been assembled at Oban on Scotland's west coast months earlier. The ships were stripped of everything valuable, ballasted for precise buoyancy, and fitted with scuttling charges. They made their final voyage under their own steam to predetermined coordinates off the invasion beaches. At the assigned moment, crews opened seacocks, detonated charges, and abandoned ship. The vessels settled to the bottom in carefully planned positions, creating an outer line of protection against Atlantic swells. The scuttling operations proceeded so smoothly that most ships settled within 50 feet of assigned positions. This precision was remarkable, given the complexity of deliberately sinking a ship exactly where intended. Current, wind, and the vessel's momentum as it flooded all affected final position. Yet the crews, many of them merchant sailors volunteering for this final voyage, executed their assignments with professional skill that would have made peacetime harbour pilots envious. The whale roadways came next. Long trains of linked pontoons and bridge spans snaked across the channel, towed by dedicated tugboats. Once in position, Royal engineers secured them to the spud pier heads and extended them toward shore. The flexible joints that Beckett had designed proved their worth as the roadways undulated with waves while maintaining structural integrity. By June 13th, Mulberry B at Arromanches had developed sufficiently to provide 2 crescent-shaped harbours capable of accommodating 75 Liberty ships and smaller craft simultaneously. The speed of construction astonished even the engineers who had planned it. Within just 7 days of D-Day, both artificial harbours were beginning to handle cargo. The first supply ships to use the Mulberry facilities found themselves in the strange situation of docking at piers that hadn't existed 10 days earlier, and harbours built from materials scattered across England 2 weeks before. Ship captains accustomed to traditional harbours marvelled at the ingenuity. Captain James Morrison of the Liberty ship Robert E. Peary wrote in his ship's log on June 14th, approached what charts show as open beach, instead found complete harbour facilities, including floating piers, breakwaters, and navigational markers, docked at Pier 7 of Arromanches Harbour, and discharged 400 tons of ammunition, 200 tons of rations, and 150 vehicles in 8 hours. The entire facility floats on the tide, rising and falling 15 feet between high and low water, yet remains perfectly functional throughout. The engineering involved defies my comprehension. Then, disaster struck. On June 19, 1944, the worst June storm in 40 years descended on the English Channel. For 3 days, northeastern winds of force 6 to force 8 pounded the Normandy coast. Waves reaching 8 feet in height crashed against the artificial harbours. The bombardon outer breakwaters, designed to absorb such punishment, began to fail. Some broke apart under the pounding, others tore free from their anchors and drifted into the inner harbours, where they smashed into Phoenix caissons and whale roadways. At Omaha Beach, Mulberry A suffered catastrophic damage. The harbour had not been fully completed when the storm arrived. Critical reinforcements and anchor systems were still being installed. Phoenix caissons cracked under the wave assault. Whale roadways broke free and washed onto the beach in tangled wreckage. By the time the storm abated on June 22nd, Mulberry A was beyond repair. The American decision to abandon Mulberry A came quickly. Surveys showed that restoring the harbour would take longer than building it originally, as damaged components would first need to be removed. Instead, the Americans salvaged usable sections and sent them to reinforce Mulberry B at Arromanches. The British harbour, more protected by the natural geography of Gold Beach and more completely assembled before the storm, survived with damage but remained functional. The storm validated the Mulberry concept even as it destroyed one harbour. At Omaha Beach, where Mulberry A lay in ruins, the gooseberry breakwater created by scuttled ships had held firm. Ships anchoring in the protected water behind the blockships rode out the storm with minimal damage. Without even that basic protection, the June storm would have scattered the invasion fleet and potentially doomed the entire operation. Lieutenant Colonel George Shadic, commanding 20 Port Group Royal Engineers responsible for operating Mulberry B, wrote in his after-action report preserved in the National Archives. The storm of June 19th to 22nd subjected our harbour to conditions far exceeding design specifications. That any portion survived testifies to the quality of British engineering and the foresight of our planners. The bombardons which failed did so while absorbing punishment that would have destroyed the entire invasion fleet had those ships been exposed to open water. Even in failure, the Mulberry concept proved its value. Mulberry B at Arromanches was substantially reinforced with units salvaged from the American harbour. The Phoenix caissons were pumped full of sand to give them greater stability, a measure that undoubtedly explained the extended service the British port rendered. The harbour that had been designed to function for just 3 months would remain operational for 10 months after D-Day. The statistics of what this single artificial harbour accomplished defied belief. Through Port Winston passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. At peak efficiency, the harbour was landing 7,000 tons of equipment and supplies daily. The port operated around the clock, with ships docking at any hour to discharge cargo. The operational efficiency of Port Winston exceeded every prediction. From June 20th to September 1st, 1944, the harbour averaged 6,750 tons daily despite damage from the storm. This figure represented dry shod cargo, supplies unloaded directly from ships to trucks without exposure to water or weather. The importance of this distinction became clear when compared to beach landing operations. At Omaha and Utah beaches, where the Americans relied on direct beach landings after losing Mulberry A, supplies were unloaded from landing ships' tank that grounded on the beach at high tide. The method worked but exposed cargo to salt water, required extensive waterproofing of equipment, and depended entirely on weather conditions. A rough sea meant no landings. Port Winston operated in all but the most severe weather. The harbour's design allowed it to handle cargo that could not be driven directly onto beaches. Heavy artillery pieces, delicate communications equipment, medical supplies requiring protection from the elements, all moved through Port Winston in continuous flow. The whale roadways proved their worth beyond anyone's expectations. Designed for 3-month lifespans, they handled traffic constantly for 10 months. Fully loaded trucks drove from Liberty ships anchored offshore directly onto French soil across bridges that floated on the tide. Royal Engineer Sapper William Hutchinson, attached to 20 Port Group, wrote to his family in July 1944. His letter, preserved in the Imperial War Museum archives, provided ground-level perspective on the harbour's operation. We work 18-hour days keeping Port Winston operational. The harbour lives and breathes like a great mechanical beast. With each tide, the entire structure rises 15 feet and falls again. We must constantly adjust moorings, inspect pontoons for damage, repair roadway sections, and guide ships to pier heads. German artillery occasionally shells us from inland positions. Luftwaffe raids occur nightly, yet the supplies flow without pause. Today alone, we unloaded 40 ships carrying tanks, ammunition, rations, fuel, and medical supplies. Everything an army needs arrives through our floating harbour. When I think that this entire port didn't exist a month ago, that we assembled it under fire from components towed across the channel, I can scarcely believe I'm part of it. The strategic impact of Port Winston extended beyond mere tonnage statistics. The harbour provided the Allies with flexibility that German planning had never anticipated. Field Marshal Erwin Rommel's defensive strategy for Normandy had been based on one fundamental assumption: the invaders would need to capture a major port within days or face defeat through supply starvation. Rommel had fortified Cherbourg, Le Havre, and other ports with exactly this assumption in mind. When Allied forces came ashore on beaches rather than assaulting ports directly, German intelligence initially interpreted this as evidence of a limited raid rather than full invasion. Even when the scale of the landings became apparent, German commanders assumed the Allies would rapidly move to capture Cherbourg. The appearance of artificial harbours off the invasion beaches shocked the German High Command. They had no intelligence warning of the Mulberry project despite its massive scope. Albert Speer, Nazi Germany's Minister of Armaments and War Production, provided the most eloquent testament to the Mulberry harbour's impact. After the war, during interrogation and later in his memoirs, Speer reflected on the Atlantic Wall's failure. His words, though coming from an architect of Nazi war crimes, captured the essence of why Germany lost. To construct our defence in 2 years, we used 17 million cubic metres of concrete and 1.2 million tons of steel. A fortnight after the landings by the enemy, this costly effort was brought to naught by an idea of simple genius. The simple genius Speer referenced was the Mulberry concept. Germany had invested enormous resources into fortifying every port along the Atlantic coast. The Nazi High Command believed these fortifications made invasion impossible without catastrophic Allied casualties. Instead, the Allies simply bypassed the fortified ports entirely, bringing their own harbours with them. This represented more than tactical surprise. It demonstrated a fundamental difference in how the two sides approached warfare. German military thinking remained rooted in 19th-century concepts of fortress warfare and defence of strongpoints. The Allies embraced innovation, willing to attempt solutions that conventional wisdom deemed impossible. The contrast extended beyond the Mulberry harbours to encompass Allied strategy as a whole. While Germany relied on static defence and counterattacks with armoured reserves, the Allies developed specialised equipment to overcome obstacles. Hobart's Funnies, a collection of modified tanks including flail tanks for clearing mines, bridge-laying tanks for crossing obstacles, and amphibious tanks for swimming ashore, epitomised this innovative approach. The Germans had technical brilliance as evidenced by weapons like the V-2 rocket and jet aircraft, but they lacked the industrial capacity and strategic flexibility to turn technical innovations into war-winning advantages. The Allies, particularly the United States and Britain working together, combined innovation with industrial mass production. The Mulberry harbours exemplified this combination. The engineering innovations from Beckett's flexible roadways to the Phoenix caissons controlled flooding systems represented cutting-edge design. Yet the project succeeded because British industry could manufacture these innovations in quantity despite 4 years of total war. Over 45,000 workers contributed to Mulberry construction simultaneously. Commercial firms across Britain diverted resources from other war work to produce components. The scale of coordination required dozens of government ministries, military services, and private companies to work in unprecedented cooperation. This organizational achievement matched the technical accomplishment. The human cost of operating Port Winston deserves recognition alongside the engineering triumph. Royal Engineers worked around the clock in all-weather conditions to keep the harbour functioning. German artillery shelled the harbour regularly from inland positions. Luftwaffe bombers attacked nightly. Yet the work continued without pause. Casualties among harbour personnel were remarkably light given the conditions. German artillery was inaccurate at the ranges involved. Luftwaffe raids focused primarily on ships and beach areas rather than the harbour infrastructure itself. The anti-aircraft defence mounted on Phoenix caisson and stationed throughout the harbour area proved effective at disrupting bombing runs. Nevertheless, the constant threat of enemy action added psychological strain to already exhausting physical labour. The engineers who operated Port Winston understood they were part of something historically significant. Many kept diaries or wrote letters describing their experiences. These personal accounts, now preserved in archives across Britain, reveal pride in their achievement, mixed with wonder at what they had accomplished. Colonel Bruce White, who supervised much of the construction, spoke at a reunion of Mulberry veterans 40 years after D-Day. His words, recorded by the Imperial War Museum, provided fitting perspective on the project. "We were young men facing an impossible task. Build a harbour that can be assembled in days, that can float yet withstand Atlantic storms, that can handle more cargo than Dover, while anchored to sand rather than bedrock. Every engineering principle we'd learned said it couldn't be done. Yet we had no choice. The invasion depended on solving these impossible problems. So we stopped thinking about why it couldn't work and focused on making it work. We tested, failed, modified, and tested again. We manufactured on a scale that strained Britain's industrial capacity. We towed floating concrete boxes across mined waters. We assembled harbour components while German artillery shells fell around us, and it worked. Not perfectly. We lost Mulberry A in the June storm. Many components failed. Constant repairs were needed, but it worked well enough. Port Winston kept the supplies flowing. The harbour bought us time to capture Cherbourg. That time made the difference between victory and defeat. Alan Beckett, whose whale roadways had proven crucial, offered his own perspective at the same reunion. "I was a young lieutenant in the Royal Engineers when they assigned me to solve the floating roadway problem. The requirements seemed contradictory. Must be flexible enough to accommodate 15-foot tidal variations. Must be rigid enough to support loaded lorries. Must be durable enough to last months in salt water. Must be simple enough to manufacture quickly. Must be transportable across the channel." Each requirement alone posed significant engineering challenges. Together, they appeared insolvable. I spent weeks sketching designs, building small models, testing them in a laboratory. The breakthrough came from watching a snake move across sand, its body flexing at multiple points while maintaining overall forward motion. I realized the roadway needed similar characteristics, rigid within each span but flexible at the joints. The torsional flexibility proved to be the key innovation. Once we had that principle established, the detailed engineering followed. Seeing the whale roadways still functioning at Arromanches 10 months after D-Day, handling traffic far exceeding their design capacity, gave me greater satisfaction than any other engineering work I've done. The long-term legacy of the Mulberry harbours extended far beyond their wartime service. Port Winston remained operational until November 1944, when the capture and restoration of Antwerp gave the Allies a proper deep-water port. The harbour's designed 3-month lifespan had been exceeded by more than 3 times. After the war, many whale bridge spans found second lives. The flexible roadway sections were too valuable to simply abandon. French, Belgian and Dutch engineers salvaged spans and used them to replace bombed bridges across northwestern Europe. Examples remain visible to this day. A whale span crosses the Nuero River in Normandy. Another crosses the Meuse River between Cannes and Maastricht. These surviving sections serve as physical monuments to wartime engineering ingenuity. The Phoenix caissons at Arromanches remain visible at low tide, marking the outer breakwater of what was once Port Winston. Local fishermen use them as navigation landmarks. Tourists visiting the D-Day beaches can see concrete evidence of what Allied engineers accomplished in 1944. The French government has designated the Mulberry remains as protected historic monuments, recognizing their significance to the liberation of France. Several Phoenix caissons dot the British coastline as well, unintended monuments to construction problems and testing failures. At Pagham Harbour in West Sussex, a caisson known as the Near Mulberry sank during towing and could not be refloated. It remains visible at low tide, scheduled as a protected historic monument. Another caisson, the Far Mulberry, broke its back in a storm the night before D-Day and lies in deeper water offshore. At Thorpe Bay, near Southend-on-Sea, a Phoenix being towed from Immingham to Southsea began leaking and was intentionally beached on a sandbank in the Thames estuary. It too achieved scheduled monument status, accessible at low tide for those willing to wade through mud to examine its construction. These failures, preserved accidentally as monuments, remind us that the Mulberry project involved considerable risk. Not every component performed as designed. Not every Phoenix reached France intact. The June storm destroyed one complete harbour and damaged the other. Yet the project succeeded because British and American engineers had built-in redundancy, created multiple solutions for critical problems, and adapted quickly when initial designs failed. The technological innovations developed for the Mulberry harbours influenced post-war civil engineering. Floating bridge technology advanced significantly thanks to Beckett's whale design. Harbour construction incorporated lessons learned about breakwater design and tidal accommodation. Concrete mixing and curing, techniques developed to produce the Phoenix caisson under wartime pressure, improved commercial construction practices. Perhaps most importantly, the Mulberry project demonstrated that massive engineering projects could be completed in months rather than years when urgency demanded. The organizational, planning and execution skills developed during Mulberry construction influenced post-war infrastructure projects worldwide. The personnel involved in building the artificial harbours dispersed after the war into commercial construction, bringing with them experience in managing complex projects under severe constraints. The contrast between Allied and German approaches to the invasion problem crystallized in the Mulberry harbours. Germany chose the obvious solution: fortify the ports so heavily that capture becomes impossible. The Atlantic Wall, with its millions of tons of concrete and elaborate defensive systems, represented conventional military thinking applied with German thoroughness. The Allies chose the unobvious solution: make ports irrelevant by creating new ones where needed. This required believing the impossible could become possible through engineering and industrial effort. It required leaders willing to authorize enormous expenditures on an unproven concept. It required engineers willing to attempt what their training said couldn't be done. It required construction workers toiling in ignorance to build components they didn't understand for purposes they couldn't imagine. The difference in mindset explains why the Allies won. German military culture valued obedience, hierarchy, and adherence to proven methods. This produced excellence in execution, but rigidity in planning. When Allied actions violated German assumptions, the command structure struggled to adapt. Allied military culture, particularly Anglo-American cooperation, valued innovation, flexibility, and pragmatic problem-solving. This sometimes produced chaos and inefficiency, but it allowed rapid adaptation to changing circumstances. When conventional solutions proved inadequate, Allies sought unconventional alternatives. The Mulberry harbours embodied this cultural difference. A German general presented with the harbour problem would have calculated forces needed to capture Cherbourg and accepted the casualties. An Allied general authorised building floating cities to bypass the problem entirely. The mathematical elegance of the solution remains striking 80 years later. Traditional military wisdom said armies needed ports for supplies. German defensive strategy depended on this axiom. The Allies responded by rewriting the axiom itself. If armies need ports for supplies, and capturing ports is too costly, then build new ports and bring them along. The logical chain was simple. The execution was anything but. It required vision from Churchill, who insisted on pursuing the concept despite skepticism. It required technical brilliance from engineers like Hughes and Beckett, who solved problems that textbooks said were unsolvable. It required industrial capacity from British manufacturing, stretched to breaking point, yet delivering 600,000 tons of harbour components on schedule. It required courage from Royal Engineers who assembled the harbours under fire. It required skill from tugboat crews who towed massive concrete structures through mined waters. It required determination from the 45,000 workers who built components without knowing their purpose. Every element had to work. Failure at any point would doom the entire invasion. The morning of June 20th, 1944, brought us full circle to where this story began. Lieutenant Colonel George Shadic stood on the pier head of Port Winston, watching supplies flow across whale roadways that rose and fell with the tide yet never stopped functioning. The harbour that experts had declared impossible was landing 6,750 tons that day. Tomorrow would bring 7,000. The mathematics of D-Day's success were being written not in battle strategy alone, but in concrete and steel, in hydraulic systems and tidal calculations, in the revolutionary concept that impossibility was merely another engineering problem waiting for a solution. German intelligence had built an entire defensive strategy on the assumption that invading armies required capture of fortified ports. The Mulberry harbours shattered that assumption. They proved that engineering ingenuity could rewrite the rules of warfare itself. More than the battles fought, more than the heroism displayed, more than the tactics employed, this willingness to attempt the impossible and make it reality decided the war's outcome. The Germans fortified what existed. The Allies created what was needed. That difference, more than any other factor, explains Allied victory in the Second World War. The artificial harbours of Normandy stand as testament to human ingenuity, to the power of innovation over conventional thinking, to the triumph of flexible problem-solving over rigid doctrine. When faced with a strategic problem that seemed to have no solution, Allied planners refused to accept impossibility. They asked how engineering could create a solution that changed warfare's fundamental rules. The answer floated off Arromanches for 10 months, landing 7,000 tons daily, sustaining the advance that would liberate Europe. It was built in pieces in Britain, towed across the Channel, and assembled on hostile shores. It survived the worst storm in 40 years. It operated far beyond its designed lifespan. It proved that the only true impossibility is accepting that something cannot be done without first attempting to do it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.